Hello, I'm Bryce, and my project involved the design and implementation of a hybrid genetic incremental conductance algorithm for photovoltaic systems. Maximum power point tracking is the approach of extracting the maximum power of PV systems through modulation of intermediary power converters and moving the operating point near the peak of the nonlinear power voltage characteristic curve. Many conventional algorithms, such as CVR and PNO, lack the ability to reliably track the global maximum power point under partial shaded conditions, which exhibit two distinct peaks. The objective of this project is to develop a hybrid algorithm, combining the genetic algorithm as a global search and incremental conductance as a fast local tracker. The algorithm works through a two-stage sequence, first entering the GA mode, which locates the high power region, then transitioning to the INC mode, which fine-tunes and regulates the operating point using less computational power. The algorithm also detects change in irradiance, which may indicate partial shaded condition, and is set to re-trigger the GA mode in this event. The hardware implementation consisted of a PV emulator board powered by a benchtop power supply, which was connected to a static 10 ohm resistive bank via a synchronous buck converter, and this was regulated using an Arduino R3. The INA219 sensor was used to measure the PV emulator board current and voltage, and two separate test setups were used for the uniform irradiance and partial shaded conditions. The first stage of this project involved the development and testing of the INC algorithm and demonstration of its limitations in partial shaded conditions. So this video shows a demonstration of the INC algorithm test lab setup, specifically the partial shaded condition, where we'll be switching between uniform irradiance conditions and partial shaded conditions. This is done by adjusting the secondary current limit value, which we've done here, and it is increased from 2 watts to around 5 watts. And here, if we decrease the secondary current limit value again down to 0.1 watts, we see that the current decreases to around 1 watt, as shown on the oscilloscope here. So this indicates that the operating point is trapped at local maxima. In the next stage, the GA algorithm was developed and tested under the same conditions as the INC algorithm, with the objective of demonstrating its ability to locate the global maxima under partial shaded conditions, in contrast to the INC algorithm. The video shows the same test as done previously with the INC algorithm, however this time with the GA algorithm, where in its current operating state we see 2 watts, and if the secondary current limit value is increased to be equalized to the primary, it increases to 5 watts, which is the same behavior observed with the INC algorithm. However, if we decrease this back down to 0.1 watts, we see that instead of going back to 1 watt, it remains at around 2 watts, indicating it's still operating at the global maxima in this condition. Finally, the hybrid GA-INC algorithm was tested and verified, combining the previously developed algorithms and using the same logic sequences. The switching conditions between the algorithms were also tested and verified in the lab. This video shows a brief demonstration of the hybrid algorithm, specifically its switching conditions going from uniform irradiance to partial shaded conditions, where the GA algorithm will be reactivated upon this condition. Here, if I play the video, it is in the current steady state, and observing the oscilloscope, we see some jumping in waveforms, which is indicating that the GA algorithm is activated, and quickly going back to the INC algorithm and its steady state operation. Results showed consistently higher power draw using the hybrid GA-INC algorithm in contrast to the CVR and PNO algorithms, with the demonstrated ability to track the global maximum power point and re-trigger the GA algorithm under the defined conditions. Voltage ripple remained in the hybrid GA-INC algorithm with a comparable magnitude to that of the other algorithms. Several limitations and possible improvements exist for the developed algorithm, including the computational load required for the GA algorithm and residual voltage oscillations in the steady state. Refinements such as an adaptive step size and wider hysteresis band and additional signal filtering may help improve these oscillations, while alternative approaches such as predictive control or machine learning based algorithms may yield greater computational efficiency. Here I would like to quickly share two key challenges I encountered over the course of this project, beginning with the voltage constraint of the INA219 current sensor, which posed a challenge in the partial shaded setup. So the PV emulator boards used in the lab were designed to operate with an open circuit voltage of 21 volts. However, since the two boards are required for the partial shaded setup, this would result in an operating voltage of 42 volts, which exceeds the limit of the electronic sensors used in this setup. So the proposed solution was to supply the boards with 10.5 volts each, resulting in 21 volts total, which, while it didn't produce the smooth PV curves we expected or wanted, it still exhibited two distinct peaks and provided sufficient test conditions for the global MPPT algorithm justification. Next, the first implementation of the GA algorithm resulted in harsh switching of the benchtop power supply. This was due to the nature of the algorithm, which chooses random duty cycle samples and thus resulting in sudden jumps in the operating conditions. This posed a risk of additional component wear due to the additional stresses. But the solution here was to implement a slew rate in the algorithm, which forced the subsequent sample to be within a predefined range. Here it was 3%, thus stabilizing the operation, but at the cost of reduced tracking speed. To summarize, this project presented the development and implementation of a hybrid GA-INC algorithm. While the algorithm still has areas for improvement and optimization, the result demonstrated reliable global tracking under partial shaded conditions and increased efficiency compared to the traditional algorithms such as CVR and PNO. Here are the references used for this project, and thank you for your attention.